Another transform is the discrete Fourier transform. So this transform is still time discrete, but now it's finite in time. So our signal has a fixed length of n samples. We can obtain the DFT as a special case of the DTFT, the discrete time Fourier transform that we've seen before, if we take our finite signal and we repeat it infinite times in the past and infinite times in the future, making it periodic with a period equals to n. Here is the equation to calculate the DFT, and we note that we have now a discrete frequency index k that goes from 0 to n minus 1, where n is the number of samples. This transform is also invertible, so we have an inverse transform given by this equation. So the DFT is discrete in frequency. It has the frequency index k, that is an integer between 0 to n minus 1. So it is periodic in frequency with period equals to n. And because we're dealing with a periodic signal in time, we have what is called the circular convolution, which is given by this equation here, where mod is the modulus, so it's the remainder of the division by n. Still applies that the circular convolution in time becomes a multiplication in the DFT domain. One of the most important properties in these transforms is to remember that a periodic signal in time leads to discrete frequency, and discrete signal in time leads to periodic spectrum. And we also have this symmetry between time and frequency, so it also holds that the discrete frequency will lead to periodic time, and periodic frequency will lead to discrete time.